All right, today we're going to dive into rational numbers. And I know what you're thinking. Math rules? Seriously? But trust me, the principles that make all of this stuff work are actually pretty cool. And to prove it, we're going to start with a mistake.
Yeah, that's right. We're not starting with some boring definition. We're kicking things off with a really common mistake. It's an error that seems totally logical on the surface, but as you're about to see, it kind of breaks the whole system.
So take a look at this. Super simple problem, right? What does 1/2 plus 1/2 equal? Now, you already know the answer is 1, but let's think about how we get there. A lot of people's first instinct is just to add straight across. I mean, it makes sense. 1 plus 1 is 2 on the top, and 2 plus 2 is 4 on the bottom. So you get 2/4. It feels right. You just added everything up. But hang on a second. We all know that 2/4 is just another way of saying 1/2. It's definitely not 1. So that super intuitive answer is just flat out wrong. And that leads to the big question. Why? Why can't we just do the obvious thing? Well, the answer is hiding in the fundamental properties of numbers. To really get this, we need a better way to think about it. So forget about memorizing rules for a second, and let's visualize them instead. Let's imagine a box. Okay, first let's get the official definition out of the way, just so we're all on the same page. A rational number is simply any number you can write as a fraction. You know, p over q. The only real rule is that the bottom number, q, can't be 0. That's it. That's your ticket into the club. Okay, now picture it. This giant sealed box. And inside this box is every single rational number you can possibly think of. 1/2, -3, 17, 22/7. They're all in there, hanging out together. So all those complicated properties of numbers you had to learn, they're really just the rules of our box. And they all boil down to one simple question. If you take two numbers from inside this box and you combine them, does the answer you get also stay inside the box? And this leads us straight to our first and maybe most important rule. It's what mathematicians call the closure property. It's really all about whether our box is sealed tight or if things can somehow escape.
So let's test this out. If you take two rational numbers and add them, the answer is always another rational number. It stays in the box. Same thing for subtraction. You subtract one from another, the answer's still in the box. And multiplication? You guessed it, stays in the box. We say these operations are closed.
But then we get to division. And this is where we find a crack in the box. If you try to divide any number by 0, the whole system just breaks. The answer isn't a rational number. It's not any number, it's undefined. It basically gets kicked right out of the box. And that one little exception is why we say rational numbers are not closed under division. Okay, let's move on to our next set of rules. I like to call these the freedom rules. They're all about how much flexibility you have when you're doing your calculations, how much you can move stuff around. Now, there are two big ideas here that people mix up all the time. The commutative property is all about the order of the numbers. Is 2 plus 3 the same as 3 plus 2? Yep. The associative property is about grouping. If you're adding three numbers, does it matter which two you add together first? Nope. But here is the crucial thing to remember. This freedom to rearrange and regroup, it only works for addition and multiplication. Just try it with subtraction. 5 minus 3 is definitely not the same as 3 minus 5. With subtraction and division, the order and the grouping suddenly matter a lot. All right, let's look at one last property. And this one isn't just another rule you have to memorize. This is a genuine pro-level move for making hard problems way easier. It's a fantastic shortcut. It's called the distributive property, and what it means is that if you're multiplying a number by a group of numbers being added in parentheses, you can distribute that multiplication to each piece inside first. It's like you're handing something out to everyone inside the parentheses. Let's see this in action, because this is where it gets good. Look at this problem. I mean, you could find a common denominator for the fractions in the parentheses, but that looks messy. Instead, let's distribute. We multiply the 3/5 by the first fraction, and then we multiply the 3/5 by the second one. All of a sudden, you have two way simpler problems that are super easy to solve and then add together. It's an awesome trick. So, okay, we've looked at our box, we've looked at the rules for staying inside it, and we've talked about the freedom to move things around. But why does any of this matter? What does it have to do with that simple mistake we made way back at the beginning? Let's go all the way back. 1/2 plus 1/2. We tried to just add across and got the wrong answer. Now, finally, we can understand exactly why that didn't work. You see, just adding straight across the top and bottom isn't a reliable system. It doesn't follow the rules of our box. The properties we've been talking about, they demand a system that is consistent, a set of operations that always work for any rational numbers you throw at them. And that's what forces us to use methods like finding a common denominator. It's what makes the whole system logical and predictable.
So if you walk away with one thing today, let it be this. These properties aren't just random rules somebody made up to make math class harder. They are the actual blueprint for a system that is designed to always work.
And that kind of leaves us with a final thought, doesn't it? This isn't just about math. Think about it for a second. Whether it's the rules of the road, the syntax of a coding language, or the structure of a piece of music, where else do we rely on a clear set of foundational rules to build complex, reliable systems that we can count on every single time?